Good afternoon, I am Mr. Ish. Thank you for joining me. This video builds directly on the material I presented in the previous video. I'm going to include the tag of that video in the information of this video. It would be advantageous to see that video before you see this one. In the previous one, if you have seen it, you know we built a general series template using the Maclaurin series. We went towards the Taylor series. We extended the Maclaurin series towards the Taylor series, and we saw two applications, one with regards to sine and one with regards to cosine approximation questions. Utilizing a functions or a functional approach, we built a general template for a Taylor series. I will show you in this and will apply to an exponential question. It's an interesting idea and interesting concept because it gives you another way of doing something. I'm drawing a function over here. You know it looks like the exponential, but this function could have been any curve applicable to any general functional form. We saw in that video, the previous video, this depiction that we have before us, we were centering everything around that 0 point over there, and the Maclaurin series template was generated from that point. Then we started pushing points towards the right. We pushed a certain x units and a certain h units. You have that x plus h generating there on the bottom, which gives rise to a specific point on your curve f of x plus h, which then helps us establish the general series template form for the Taylor series. I showed you what would result in the previous video, and I'll write it out for you. The series, when centered around this x plus h, it would give you a template of this form. You'd have your original function. Why would the original function be? Because the zero order derivative of a function is equal to the original function. Here you'd have h to the power of 0, 0 factorial, which are meaningless. The next item would be your first order derivative of that original function. Then you'd have h to the power of 1 over 1. The next item would be the second order derivative, and then you'd have h squared over 2 factorial. Then you'd have a third order derivative with regards to that original function, h cubed over 3 factorial, and you can see on and on it goes. And you know this because you've looked at something which looks like this. N is equal to 0. You have up to infinity. The Maclaurin series template comes out like this, x to the power of n. If you adapt this to what we're seeing, you end up with that. Remember, again, we're adapting or we're extending a Maclaurin series towards the direction of a Taylor series, and we're giving you a general series form which can be applied to many different function forms or types, except here I'm applying to exponential. What is my eventual goal for this video? I want to evaluate or approximate a value of e cubed. I can do this for you on the calculator, and it's not hard. You do 3 and you bring in the exponential, you have 20.0855. I want to get a value close to this, 20.0855, and I'll do that by means of approximation. My approximation will involve the general Taylor series that I will develop utilizing this form. And what do I do from here? I've already generated a template over here. What do I do from here? I have to understand what it is I'm looking with regards to, which is this, but how am I looking at that with regards to this, f of x plus h. If I'm looking at e cubed, I'm really looking at e to the x plus h. But what is this x plus h? They could be the sum of any two numbers or the difference of any two numbers, which will give you a 3. I will use e to the power of 1 plus 2. E to the power of 1 plus 2 is equal to e cubed, which is equal to that. But when I'm looking at this, I'm looking at f of x plus h. This right here will feed into that template. I have an x, I have an h. Wherever I have an x in that template over there, I'll be putting a 1. Wherever I'll have an h, I'll be putting a 2. You remember this technique or this style of technique if you've seen the previous video. Now, why did I use the exponential? Because when you look at its derivative, it's still e to the x. If you look at the first, second, third, fourth, fifth, sixth, whatever order derivative of exponential, it is equal to e to the x. But notice how the Taylor series I've developed for you, or the general template for the Taylor series, has gone up to n equals 3. When I'm doing this approximation, I'm going to take it up to n equals 6. I would like to take it up to n equals 6 because I'll get a better answer over there. Now, how will I do it? Remember, in all instances, these are your derivatives receiving the x value. So let's start building it. My original value here, or my derivatives, will always be e to the x. The x is always 1. It'll always be e to the 1. Now I'll have h to the power of 0, which is 2 to the power of 0 divided by 0 factorial, which is just a 1. My next item will still again be e to the 1. Why is it always e to the 1? Because again, the derivative of exponential, no matter what order it is always the same as the original function. Here I'll have h to the power 1, 2 to the power 1 divided by 1 factorial. This right here was 0 factorial, which is still equal to 1. My next item is here e to the 1, which is my n equals 2 step. I'll have 2 to the power of 2 divided by 2 factorial, and I'll put 2. I won't put factorials here anymore. I'll actually put the actual number over here. Here it'll be e to the 1, then it'll be 2 cube. I'm here at this step, divided by 3 factorial 6. But remember I said I want to go up to n is equal to maybe 6. Let's do that. E to the 1, then I'll have 2 to the power of 4 divided by 4 factorial 24. Then e to the 1, which is always my this part, the derivative, the nth order derivative with the a value here coming in. Here the a value is x equals 1. 2 to the power of 5, because here I'm looking at n equals 5, step, divided by 5 factorial 120. 0, 1, 2, 3, 4, 5, and I'll add one more. E to the power of 1, it'll still be that. 2 to the power of 6 divided by 6 factorial 720. If I were to do computation of all of this, I should get a value close to this. And remember, this 720 came from 6 factorial. So let's start doing it. We can probably use algebraic techniques to simplify this out. I know I have 2 to the power of 0 and 1. This cancels out. I am left here with nothing but an e. Here I'm having a 2e. Here I'm having a, this will cancel out with that to give me a 2. I'll have a 2e generate. Here I'm having 2 to the 3 divided by 6, which is 8 divided by 6, which is a 4 over 3e. When I look over here, I have a 16 divided by 24. 16 divided by 24, 8 goes in both of those numbers, and it'll be 2 over 3e. Now let's look at this. I probably won't do any fancy simplification over there. I'll just keep it 32e over 120, and then I'll add this. You see this value, the n equals 6 value, I'm going to erase it, but I'm going to bring it right over here in its final form. It would be 64e divided by 720, and that's what I'm adding over here. 64e divided by 720. Some of these we can add easily, some of these will require the calculator. I can add all of this easily. This is equal to 5e. I can add this easily. 4 over 3 plus 2 over 3 is a 6 over 3, which is a 2e. I'm getting a 2e from there. Now I have to just add this. I'll take this in terms of a denominator and I'll add it to this, which is, as you're seeing here, is 7e. This right here comes from all of this is equal to just 7e. Let's work here from the right hand side, go towards the left side. We're looking here at 1, that's my e, times 64 divided by 720. I'm going to save this value. Now let's look at this. We look at the e part, we'll multiply it by 32, we'll divide it by 120. I'll add it to that value right there, and I'm getting here a 0.9665, but I can add this easily. I'll add it plus my e value times 7, and I'm getting 19.994473. Let's bring it out and let's put it here. I'm getting 19.994473. If I go up to n equals a bunch of higher numbers, I'll get this value creeped up towards 20. Right now, you know, I went up to n equals 6. Had I gone up to n equals 4, I would be further down. My margin of error will be worse. Let's calculate what the actual margin of error is. I have this value here, and I'm going to bring out the exact value, e cube. It's that. Let's save this value. Let's take that value, 19.994473, minus that saved value, which is a true value, divided by that true value, multiplied by 100. My margin of error is minus 0.4533%, which means I'm underestimated by 0.4533%, which is not bad. I'm looking at a margin of error here of minus 0.4553%. A very good value here, but again, we went up to n equals 6. I have a good feeling if I went up to n equals 9 or n equals 10, I'd creep up closer. But remember, as you're adding more and more n values, the individual numerical value of those items becomes increasingly small, because you end up having these large factorial outcomes here on the bottom, and it brings everything down to a small number. So you get these minuscule additions as your n values increase, but our margin of error here is good. But look what we've done here. In this video, we started with the concept of extending the Maclaurin series to the Taylor series. As we saw in the previous video, we used that same concept over here. We built a series around x plus h, a general Taylor series. This right here is a general Taylor series. We brought the approximation for e cube into that, and we have come up with that value. You can do this exercise here for a bunch of other functions. You can do that on your own. If you wanted to look at e cubed, you could have done that in this other way. You could have done e to the power of 4 minus 1. It's still equal to an e cube. Here your x would be equal to a 4, your h would be equal to a minus 1, and then you'd run this 4 and a minus 1 into this template, and you should get a good outcome with that as well. But that's it for this video. Thank you for watching.